The advice view. We close this chapter with some brief remarks about an alternative view of being FPT provided by an analog of the classical notion of advice introduced by Karp and Lipton. Aside from the easy result below, in this section we do not pursue the advice view further. Rather, we offer it to the reader as an alternative view that might shed some light upon the basic definitions. We will look a little more closely at the advice view in Chapter 5. The reader concerned with the concrete problems may well wish to proceed directly to the next chapter. The classical advice class P over poly is concerned with languages that can be recognized in polynomial time when we are provided for input of size, the size of x equals to n, a word of advice Wn, where the length of Wn is bounded by some polynomial, Q of n. Notice that the word of advice depends only upon the size of x equals to n of the input, not what x actually is, and hence a single Wn works for all the summations to the n strings of length n. In Chi, Chain, Downey, and Fellows, it is proven that non-uniform FPT is exactly the set of problems solvable in polynomial time using a finite piece of advice f of k for each slice k. So the whole slice Lk uses the same piece of advice. Theorem 2.5, Chi, Chain, Downey, and Fellows. 1. L in FPT non-uniform if and only if there is a polynomial time oracle Turing machine phi and a function f which maps from n to sigma star such that for all x and k in L if and only if phi to the f of k of xk equals to 1. 2. Furthermore, L is in FPT strongly uniform if and only if there is a polynomial time oracle Turing machine phi and a recursive function f which maps from n to sigma star such that for all x and k, xk in L if and only if phi to the f of k of xk equals to 1. Proof. 1. The proof is easy. Let L in non-uniform FPT. Then there is a sequence of procedures mk, a constant c, and a function g such that xk is in L if and only if mk of xk accepts, and m runs in time g of k times the size of x to the c. Consider the following new machine phi accepting L. This machine runs in time x to the c plus 1. Now we know that f of k times x, the size of x to the c, is dominated by the size of x to the c plus 1, and so there is a string x equals to 0 to the n for some n by which the size of x to the c plus 1 is greater than 2 times g of k times the size of x to the c. Once this n and an index e of k of the procedure mk are known, we can write all the values for L of xk for the size of x less than equals to n in the table T. This is the advice. We define f of k equals to n e of k t under suitable encoding. On input xk, phi first sees if the length n of x exceeds the length of those on the lookup table f of k equals to t. If the length exists n, then the machine emulates mk of xk. Otherwise, the machine phi uses table lookup to give the desired answer. Conversely, if phi and f exist for L, then we can reverse the above process to get a non-uniform FPT algorithm running in time p of xk plus h of k for some function h, where p is the running time for phi. The proof of 2 is similar, except that now we can recursively compute everything. We do not pursue the advised view further here, but offer it to the reader as an alternative view that might give some further insight into the basic definitions. We will look a little more closely at this in Chapter 5. Historical notes. Ever since the discovery of the fact that many natural problems are seemingly intractable, authors have looked for feasible partial solutions. We refer the reader to Gary and Johnson, particularly Chapter 4. In that chapter, Gary and Johnson look at what they call analyzing subproblems. The reason for Gary and Johnson's interest in subproblems is encapsulated in the following quote. If a general problem is NP-complete, we know that an exponential time algorithm will be needed unless P equals to NP, but there are a variety of ways which the time complexity of an algorithm can be exponential, some of which might be preferable to others. In retrospect, it is obvious that many authors have devised algorithms which demonstrate the fact that the parameterized problem is FPT. For instance, as we will see in Chapter 4, all pseudo-polynomial time algorithms actually demonstrate the fact that the relevant problem is FPT. To our knowledge, the first author to explicitly note the fact that SK varied. Problems such as dominating set seemed to take time omega of n to the f of k with the f of k goes to infinity was Ken Reagan in some comments in one paper. The first paper to address the asymptotic fixed parameter complexity of parameterized problems, i.e. the behavior sk goes to infinity, was Abrahamson, Ellis, Fellows, and Malta. Roughly speaking, those authors look at the comparison between languages that were non-uniformly FPT and those that were P-complete or dual P-complete by the slice. There are a number of severe limitations and other more technical problems with the Abrahamson et al. Approach. Those authors certainly would not address comparisons of the parameterized complexity of, say, vertex cover and the dominating set, nor parameterized versions of the problems outside of NP. The basic definitions of this chapter were given in Downey and Fellows. The advised view is taken from Kai, Chen, Downey, and Fellows. We will give more detailed historical remarks concerning the issue of fixed parameter tractability versus intractability in Chapter 9 of Part 3, where they will be more in context. We will also give historical comments concerning the various techniques examined in this book in the relevant chapters and sections.